lectures, Attosecond physics near future prospects, because each one is dealing with experimental capabilities that experimentalists claim they will have soon. And in my group, we have said, well, assuming they achieve what they're trying to achieve, what new physics will be observed? So that's the motivation for what we do. And in the first lecture, I told you what can be done and what can be learned if attosecond pulses become intense. Okay. This lecture is something completely different. I don't think anybody is in this field, but it will be a new area of attosecond physics, which is when one achieves attosecond pulses of electrons. My third lecture will deal with what can you do with circularly polarized attosecond pulses, but that will be on Saturday. So, as outlined, since this is new to most people here, I'm going to give some background and our personal motivation. And then show you what we did initially to treat ultrafast electron diffraction as a potential scattering, then to treat it correctly as coherent scattering, and then how to improve on results for coherent scattering with energy resolved scattering. But I go back to the title. The key motivation of attosecond physics is to image electronic motion. In the hydrogen atom, if you just use the Bohr model, you can easily calculate that an electron orbits a proton in approximately 152 or so attoseconds. So if you, and all chemical processes, when two atoms combine to form a molecule, or if you excite a molecule to make some sort of chemical transformation, the electrons are moving on a hundreds of attosecond time scale. The question is, can you observe such motions? That's a key motivation of attosecond physics and of this talk. So, let me, first of all, since this is electron scattering, we're looking at short electron pulses versus optical pulses. Let me say that electron scattering is about 1 million times larger, has about 1 million times larger scattering cross-sections than photon cross-sections. So this is something that is valuable. Furthermore, for electron scattering, elastic scattering dominates. So we heard from Linda's talk that when you do at LCLS these X-ray scattering experiments, the idea is to image before you destroy. Because as I will show you, the X-rays really damage the targets, and but for electron scattering, the elastic scattering dominates, so you don't do as much damage. The spatial resolution is also better. For example, a 10 keV electron has a wavelength of 1/10 of an angstrom, whereas a 10 keV photon has a wavelength of 1 angstrom. So you have better spatial resolution. I don't know if you can see this. I had to transfer from one PDF file to another here, but this is a review in 2006, which is taking data from a paper in 1995, but it summarizes very nicely a key difference of electron versus optical pulses. That is, if you have electrons anywhere in the range from 80 keV to 500 keV, or X-rays of 1.5 angstroms, which corresponds to 8 keV of energy, the ratio of inelastic to elastic scattering events for electrons is about 3, whereas for X-rays it's about 10. So you get 10 inelastic scattering events for every single elastic scatter. Moreover, for each of the inelastic events, electrons deposit about 20 electron volts, whereas X-rays, if you absorb an X-ray in some event, it's 8 keV, so you absorb 8 keV of energy. And now, if you look at the energy deposited per elastic scattering event, which is what you want because that doesn't destroy the target. If there are 3 inelastic events for every elastic scattering event, for electron scattering you deposit about 6 keV in your target, whereas with X-rays you deposit 80 keV. So the energy deposition is much greater. Now, that said, there is an advantage to X-rays because the elastic mean free path for an electron is about, if you call that 1, then the mean free path for X-rays is about 100,000 to 1,000,000 times better, which means if you have thick samples, you really need X-rays to image it. Electron scattering is for thin samples, and so on, or isolated molecules. Our motivation is based on discussions with my colleagues at Nebraska. In 2009, which is when we started thinking about these issues, my colleague Herman Bachmann and Nobel laureate at Caltech, Ahmad Zewail, wrote a National Academy of Sciences paper on a scheme for producing ultra-short electron pulses. And the idea is very simple, that you shine a laser on some metal tip, for example. The laser is oscillating at 2.5 femtoseconds. And so every time the electric field is pointing this way, you get an electron pulse out from your metal tip. And that pulse is now moving with some energy. You've all studied first-year quantum mechanics, I hope. And you know that if you have an electron wave packet, what does it do as it propagates? It spreads. Okay? So you have a spreading wave packet, and that's a problem because you want a spreading wave packet means the time over which it overlaps a target is very big. And if you want to stop the motion of electrons in your target, you want your electron pulse to be very narrow in time so that you pick a particular instance at which you sample the target. That's where the electrons are moving. So what do? Well, in this paper, they proposed some scheme. I'm not an expert on how you would do this, but it would be some laser mode that you send in that with the electron pulse here, you have this Ponger mode of potential, and the slow electrons slide down this potential and get sped up. The fast electrons here, on the other hand, see this rising potential and they get slowed down. And so you have this pulse, and as it's moving along, the slow electrons are catching up, the fast electrons are slowing down. Right on the target, you have them overlap so that you have the narrowest possible electron pulse. And in this paper, my colleagues, they may have written another paper in which they developed a thin lens type formula to predict exactly where you put your target so this optimum condition applies. More recently, we hired another faculty member, Martin Centurion, from NPQ in Garking, and he also does ultrafast electron work, and they wrote this applied physics letters proposing some scheme of using magnetic and electric fields to compensate for the dispersion, which is a fancy term for getting this pulse to be narrow on a target. And this shows you how they use the fields to act on different components of a wave packet and then make them combine on your target to a narrow pulse. So, after discussions with my colleague Bachmann in 2009, I had a new graduate student and I said, look, this might be interesting. Suppose experimentalists succeed and make attosecond pulses. What could you see? Electron motion. So that's what motivated us. And of course, if you just want to see, if you're going to see anything, you do the simplest possible theory you could possibly do. You don't worry about all the complications, because if something is not going to work, you don't want to spend a lot of time on it. So we treated the electron diffraction in the simplest possible way. And because this was one of the first papers, of course, it immediately got into Visitor Letters with a lot of discussion with the referees about taking into account variations of experimental parameters that made our images much worse than they were if we just assumed fixed experimental parameters. I'll show you that later. But the experimental setup we imagined that we tried to simulate was the following: that you have a laser and you have an atomic beam. And of course, for proof of principle, we chose an atomic beam of hydrogen atoms, because then we could work out a lot of this stuff analytically. And this laser pulse excites the hydrogen atom to a coherent state that beats. And I'll show you what that means in a second. So this coherent state is beating, and after some time delay, after you excite it, you hit it with the electron pulse, and you get a diffraction pattern for these electrons. They have an angle phi in the scattering plane, and they're scattered by an angle theta. These are the key parameters of our system. We're choosing 10 keV electron pulses because my experimental colleagues said, oh, that's very easy to do, to make. And we chose a pulse width of 110 attoseconds because that was one of the examples in the experimental paper proposing how to build attosecond pulses. For this energy, the wavelength of the electrons treated as waves is 1/10 of an angstrom. We assumed an angular divergence of our electron beam of 10 to the minus 3 radians, which is what my experimental colleagues told me is reasonable. And these are the two time-varying targets we chose. For hydrogen, we chose a linear, coherent superposition of the 3p and 4p state. And for the theorist's molecule, H2+, which Brett Esri fortunately talked about, we proposed a linear combination of the sigma Gerada 1s and the sigma Ungerada 1s wave function, which André Bandrauk had proposed to experimentalists as an interesting superposition. He never said how to produce it, and so we didn't either. But it was in the literature, and so we adopted it. For the hydrogen case, we gave explicit guidance as to how to produce this linear superposition. Because we wanted an equal population of 3p and 4p. And so it turns out if you use the 8th harmonic of a Ti-sapphire laser, that gives you an energy of 12.45 eV, which is right in the middle between the 3p state and the 4p state. You have hydrogen in 1s, one photon transition takes you to a p state, and this will take you right between the two. If you now plot the pulse, using time-dependent perturbation theory, you plot the pulse duration as a function, you plot the population of all the p states as a function of pulse duration, you find, you probably can't read this, but this is the 3p population, this is the 4p population, This is the 5p population. This is the 2p population. You see, if you take a pulse duration of about 8.7 femtoseconds, the population of 3p and 4p is equal, and the population of other nearby p states, 2p, 5p, is 0, essentially. So this is what we proposed. And then we use this simple firstborn that you learn if you study scattering theory still in quantum mechanics. It's not as often taught, but it should be. In firstborn, you treat the target potential as a charge density. You add up all the electrons in their state, and you scatter from this charge density, and you get this scattering amplitude, which is a Fourier transform. If you treat the incident and scattered electrons as plane waves, it's a Fourier transform of the charge density of your target, and you find that the differential cross-section for your scattering is the absolute square of this amplitude. That's the simplest possible theory for electron scattering. And this is what we get. This is as a function of time delay. So the time delay here means that the electron and the laser pulse have no delay. So this is what along the z-axis, this is the linear combination of 3p and 4p states, and this is the diffraction pattern. As you increase the time delay between the production and the sampling of the target, or pump and probe, make this T/4, where the beat period of these two is about 6 femtoseconds. Then you get this diffraction pattern. If you have a time delay of half the beat period, this is what the charge density looks like, and this is the diffraction pattern. So what's happening here, 3p has, in the Bohr model, has a radius of about 9, and this has a radius of about 16. The square, it goes like n squared. So you have what's called a breathing mode. As you beat this coherent state, the 3p state with a radius of 9 expands to the 4p state with a radius of about 16, with a period of about, I'm forgetting now, but the period is it's around 6 femtoseconds, and you get this breathing mode, and that's reflected in the diffraction pattern. For the H2 plus linear superposition of the states here, we chose a fairly large radius, the same as Andre Baldrag chose, of around 6, where the slopes are not so great, and therefore the heavy particles. Yes?
There's a question. Sorry.
Yes?
Oh, sorry, just the previous slide. So did you assume that the so-called orientation of the nuclei?
We assumed that well, for hydrogen, you don't have an orientation. It's spherically symmetrical.
What are the two? Oh, okay.
For the next problem, I'll tell you. I will say about.
What are the two blobs? I'm sorry. What are the two blobs there? Then what's the spatial structure?
This is, we're plotting along the z-axis. So this is the scattering of the incident electrons from hydrogen. Some scattered this way, some scattered that way.
And how does like?
And this is the z-axis in the scattering plane. So you have your image, you have your target, you have the electron beam. The electron beam has some width, it scatters like that, and on the plane of scattering, this is what you observe. Well, no, this is what you observe. This is the way the target looks, the charge density of the target in the z-axis.
Okay. I see. Okay.
The direction on that was chosen by the excitation pulse, though, right? The
Yes,
alignment of the peak.
yes, yes. Yeah, the excitation was linearly polarized along the z-axis, and that determines. So here for hydrogen, we chose 6 AU separation, which is, and the referees insisted that we take into account variation, so we took 5% variation, which is much greater than what would normally happen in this state over the time period of our pulse. The alignment to the beam is 90 degrees, so we assumed that the H2 plus molecule is perpendicular to the incident electron beam, but with a spread of plus minus 20 degrees. And the beat period is 7.9 femtosecond, so a 110 attosecond pulse can resolve electronic motion. This is what the charge density looks like. Here at t equals 0, one is on one nucleoside. As you increase to t over 4, the beat period over 4, you have a coherent superposition of electron density on both nucleosides, and then the electron hops to the right side, and then as you keep going, you get this again and back here. You see here that this varies in time. For this period, you can barely see there are minima. If we didn't do all this averaging that the referees insisted we do over the bond length, over the alignment angle, these are beautiful white lines here. It means this is two-slit diffraction, because the electron comes in, it sees two targets, and you get interference that cancels any amplitude in these regions, and that's visible here. Is there a minimum of the scattering there? But notice that in Born approximation, this scattering picture is identical to that one. It can't distinguish electrons on the left or the right. This is a problem with Born approximation. Yes?
I think I missed where you explained it, but how does the time resolution of the electron bunch come in? I mean, in the Born approximation, that's a plane wave, right?
Yes. So we have an electron pulse. We treat it as a wave packet, and we treat the scattering at each electron in our wave packet. So it's some spread of about 20, 30 eV, about 10 keV, and we treat for each energy as if it were a plane wave.
Okay, and then superimpose those to get
Yes.
your wave packet.
Yes.
I see, okay.
Okay, now that got into PhysRev letters. It got a lot of play. Peter Baum at Garking, who's one of the experimentalists working on such things, told me that paper greatly encouraged him because it indicated that his effort to try to get these short pulses would allow him to do good science. But the Born approximation, it has problems because it, as we said, it can't distinguish asymmetries. And so, given that you should be able to see something, we try to refine the theory and do a more proper theory, which is to look at coherent scattering. And we were motivated, this is the paper, it's a long paper, in which the theory is given. And we were stimulated by one of Francis Robichaud's paper, which I will quote in a few slides. Francis Robichaud told us that we were the first citation to his paper. So here is the scheme for ultrafast electron diffraction from a coherent state. I'm going to show you for the hydrogen atom, because when you deal with the coherent state, the calculations are much lengthier. We had to go to supercomputers and so on. But we still have 100 attosecond electron pulses, 10 keV. This is the bandwidth, this is the wavelength, a spread of 10⁻⁴ radians in the incident beam. and we're looking at hydrogen targets, I'm going to show you breathing modes, wiggling modes, and a hybrid mode. And the bottom line that I will conclude with is that these short electron pulses can image electronic motion despite the problems that arise. And the problems that arise is that if you want to treat the scattering properly, here's Francis's paper in 2000, and this is our paper in 2013. If you want to treat scattering properly, classically, you have a particle coming here, you have a target here. In Born approximation, you have a plane wave, which isn't localized anywhere. So the proper quantum wave, whoops, sorry. The proper quantum way to describe scattering is to treat both the target and the incident electron as wave packets. We have here a superposition of atomic states on the target. This is for the breathing mode I showed you, 3p and 4p. This would be just 2, n equals 3p and n equals 4p. There's a wave packet here for the incident electron with momentum k0, but spread around 10 keV by about 20 electron volts. The target also has a spread. So they're both localized because of this wave packet, and you have to sum over the momenta in these wave packets. That's your coherent wave function. And I don't want to go through the lengthy theory. It takes, I have about 20 handwritten pages of notes checking what my student Shao did. And the bottom line, however, with reasonable approximations, is very simple to understand. And let me emphasize this, that you want a differential scattering cross-section. Your superposition state is the sum over Cn with your target states n here, and they have a time dependence like that. T is what causes the interaction. In electron scattering, it's the electron correlation. For our hydrogen targets, it's the incident electron against the nucleus and the electron of the target. So you have to work out this transition matrix element. Then you go to some final state of the target and the scattered electron n. The coherent state gets summed coherently. Then you square this for transition to a particular final state that you can measure, and then you sum over all those final states. So this is the coherent state of the atom that comes into the right-hand side of this matrix element. And you can see that what the scattering process measures is this coherent state as probed by this interaction, which is the Coulomb interaction. And I'll show you that this actually relates. I want to plant in your mind this now. You can show that this relates to the momentum wave function of the target. So if you're trying to image target electron wave functions, it's the momentum space wave function that's important, as I'll show. So this is a picture showing you the breathing mode of this superposition 3p and 4p. I'm sorry, I didn't write the time dependence of the breathing mode. It's 5-something femtoseconds. But you see it expands and contracts, and whoops. And so now, I forgot to emphasize here. what this does here, this sum over M, is you have to sum over all final states within the